Okay, Assalamualaikum and good afternoon. So we continue our tutorial here. I share you my slide there, and I hope you could make your own notes. You could print screen. You could snapshot the screen, and then you could might be paste on your words and create your own PDF. And I also upload this video in my YouTube channel. So I hope you could find your own time to watch this again. And I think you already have the textbook in PDF version. So I hope you could make some revision of this. And our aim objective is actually for chapter 1, 2, and 3 is I hope you could use the Navier-Stokes equation. So we have a lot Navier-Stokes equation for R axis, theta axis, and also the Z axis. And I hope you could use that. You could suit with the application. You could do the integration and so on and so forth. Okay, yesterday we focused on this question. So I already explained about the power of n here. So and then I think for today we will go for question number 2 here. So in this question, consider the axial co-wave flow as shown here. So in your textbook, it is figure 3.3. With both cylinders moving, find the velocity distribution UR and plot it for U1 equal U0, U1 equal minus U1 equal to U0. Okay, so for the plot here, so I don't do that. You could do that if you want. But as I said, we are focusing on the way we choose the equation, the way we do the derivation and so on. Okay, so this is the two cylinders. Oh, I hope you could imagine that this is actually something like this. So we have a cylinder here, and then we have another hollow cylinder. So and then whether this cylinder is moving at certain velocity or both of this cylinder is moving at certain velocity. So it's depend on the question. So in this situation, okay, please assume that we will do this by using the polar coordinates. So please prepare the continuity equation for polar coordinates and also the Navier-Stokes equation. So for Navier-Stokes equation, please bear in mind that in this situation, we have 3 axes actually. So for sure, we have the Z1. So we have the Z here. And then we have the R. And also we have the theta. So the theta is, okay, for example, this is the 3-dimensional view. So this is the same. So let's say this is the center point. Okay, so this is the d theta, and then the tangential velocity. So if you have one point here, so the velocity of this direction. So I hope you could imagine that this will reflect the direction of molecule, because maybe the molecule move on Z axis, or it will move to the R axis, the radial axis, or it will rotate along the cylinder like this. So if the molecule will rotate like this, so it will move with a component velocity of theta. Okay, so this is the continuity equation for polar coordinates, and this is the Navier-Stokes equation for cylindrical coordinates. So I always use it as a polar coordinates. So for compare with the Cartesian coordinate, the Navier-Stokes equation for polar coordinates is quite complex. So I will give you the equation in the final exam if necessary. So but I'm not sure whether this online exam I should give or you should take from your own notes, because somebody says that a final exam for the online version is some kind of half open book. So mean you are allowed to check your notes, and then you need to answer that question. Okay. So first step that you need to understand is you need to understand which equation that suit with your application. So in this situation, we found that if we have one cylinder like this, so if we have one cylinder like this, and then we have another cylinder, okay, like this. So and then for sure it will move like that, and then because the question is asked to find the velocity distribution of UR. Okay, here please use your creativity to understand the question. So the question asks you to find the velocity distribution of UR, means the velocity of U in the R direction. But the application must be work for Z axis here. Because when it moves Z axis here, okay, if we take the side view, so this is the outer cylinder and this is the inner cylinder. So you will find that, okay, the velocity distribution may be like this. So for example, that the velocity at the bottom cylinder here is equal to 0, and then the velocity will equal to u naught, for example, and then the velocity distribution will become like this. So this is the velocity changes, mean the velocity at this point will different with this point, at this point, and this point. So means that the velocity distribution, they are changes of velocity in term of r axis. That why the question asks us to calculate the velocity distribution for u r. So it doesn't mean that when you need to to determine the velocity distribution for r axis, so the motion should be in r direction. Okay, I hope you should understand the words of velocity distribution of this one. Okay, so and then we focus on the z-axis here, okay, because the nature of the application is now moving on the z-axis. So and then the second step is, I hope you could understand each parameter in Navier-Stokes equation and try to simplify your terms, because in Navier-Stokes equation there is a lot of parameter. They will have pressure, they will have gravity, and so on and so forth. So here we take as, okay, normally people will take the flow is a steady flow. So steady flow means there are no changes along the time. So everything with dt is actually will equal to 0. That's why we take uz over dt is equal to 0. So and then because we assume that there is only one motion here, so means that there is only the motion of uz. So we could take du d theta is equal to 0. And then du dz is also equal to 0. So what is the meaning of du dz is equal to 0? Means that, so if we have a cylinder like this, so this is the z-axis, so means that the velocity at this point and velocity at this point is remain constant. So means we don't have changes along the z. Okay, and du d theta is equal to 0. It shows that, okay, there are no rotation element of this motion. So means that all the molecule here will move in z direction. There is no molecule that contribute to the motion of theta axis here. So we could equal to 0 here, equal to 0 here, and then we have du dt is equal to u here. And then, okay, we have another du dz, we have another du d theta here. And then, okay, so about du dr here. So please make sure that as I explained previously, so the velocity in term of r rad axis here, so it's change because there are no slip condition and so on and so forth. So means that the du dr here will give you certain value, but the ur here is 0. Okay, the ur means the element of this molecule move in R direction. So you must understand that if the UR here is exists, if the component of UR is exists, the molecule cannot, okay, let's say we have the element like this, so the molecule cannot flow straight on z axis. So it will become outer and outer and outer because it will go outside. Okay, because in one molecule they will have the z velocity and also the r velocity. So means that the resultant is like this. So means the streamline is not straight like this one. Okay. So that's why we assume that there are no UR in this situation. So means that all the function here will become 0. And then because we are dealing with the z axis, so the gravity can be neglected. So we have 0 here, and also we assume that the very straightforward assumption is when the velocity is constant. Okay, we know that the dz is uh, equal to 0 because we are neglecting this one. We also neglecting this one. Okay, so it means that the velocity is constant, so means the pressure is also constant. But as I said, we are focusing on liquid in this course. So as you know that the simple Bernoulli assumption, the Bernoulli equation is if the velocity increase, so the pressure will be decreased. So but what happened to the pressure if the velocity is constant, so the pressure is constant. So so we don't have any pressure, and then we assume that the density here is also constant. Okay. So and then what we have now is actually this term. So and then we bring 0 is equal this term, and I think you already know what to do because we have two times integral differential, so we need to integrate it two times. So for the first time you will get 0 here, and then please be careful, if you integrate the 0 you will get constant value, and then if you integrate another one, so you will get another constant here. So then you could say that your UR, so this is equal to UR, so UR is now equal to C1 ln R plus C2. So what you need to do is you need to determine what is the value of C1 and what is the value of C2. So how to determine this? So again, we need to depend on the boundary condition. So boundary condition is actually not something that you need to remember. It's depend on the situation. So what you need to do is you need to go back to the application, and then you start to point where are the boundary. So the boundary is the boundary between the fluid and the solid. So this is the boundary, the in layman terms, so this is the boundary between fluid and solid. So you take these 2 points, the condition of these 2 points. So in this situation, because the coordinate system is in R, and we'll use R as the coordinate system, so you just say that this is R equal to R0, for example, and then you will write the U is equal to what value. So in this case, so we have the R0. Okay, we have this one. Okay, at condition 1, at the bottom, at the below, so we have R equal R0 and U is equal U0. And at the top, so we take R equal R1 and U is equal U1. So you substitute in the calculation and so on and so forth. So finally, you will get this one. And then you could rearrange, you substitute the value of C1 and C2 in this general equation. Okay, so this is the general equation that we get previously. So we substitute with the C1 and C2 here. So finally, we will get the final terms of the UR is like this. Okay, so what is the usage of this one? So this is actually the equation for a graph. So means that if you want to show what is the velocity distribution for that application, you just you can draw or you can create a graph. Okay, and then you could know the distribution of the pattern of the velocity profile. And then if you mention, if you put, because we have R here, so and then if you give R here is the value. So for example, here is R equal to 4 and this is R equal to 10. And for example, you give R is equal to 7, for example. So and then might be you are calculating the velocity at this location. So now you will know the velocity of this molecule when you substitute the value of R equal to 7. So this is the idea of velocity distribution. Okay, again, so let's say in question 3.5, so it used the same diagram of previous question, but here the situation is your cylinder is rotated at certain velocity. So means now, as I said, we have a cylinder here. Now the cylinder is not moving on the z-axis, it rotates at certain velocity. So if you read, you can understand that a circular cylinder of radius r is rotating at steady angular rate. So the word steady means the velocity is constant, so there are no changes in terms of time. Okay, and then they will not have the constant p and so on and so forth. The density is constant, the mu is constant. So and then what we need to do is we could simplify everything. So again, it is a steady state. So everything about the t here, there are no changes along the t. So as you could see, so here I show you the expand of dt, d dt. So this is the term of d dt. And in this equation, I just simplified as capital D over dt. So and then if we have a u theta here, so actually if you want to expand this one, it will become like this. But you need to substitute the value of uz with u theta. Okay, and then as I said, the Navier-Stokes equation for the polar coordinates is quite complex. So in this, in theta axis, you will find that it has one extra terms. Okay, you could get it from my notes previously. Okay, let's say we have this is the Navier-Stokes equation for z-axis, and this is the Navier-Stokes for the theta axis. You will find that this term is actually the du over dt uz. Okay, that's why we substitute everything with the uz here. Okay, and then same. So if we write du theta over dt, so and then we have everything in u theta here. Okay, however, it has another term which is minus u theta over r. So okay, please be careful on this term because okay, if the situation is in steady, so mean you only could zero. You could make zero assumption for only du theta over dt, but you must make sure that the value here is equal to 0 or not, because the u theta over r is not equal to 0 actually, because you know, so we have a u theta here at this direction, and this u theta is actually different between this u theta and also the u theta at the below. So mean the changes from here to here and here is actually the u theta du theta dr. Okay, so in this term, okay, so in this term, so means that the u theta ur is actually not d, not delta, not the differential term. So means you need to substitute the value, but the value of ur here is actually constant. So means there are no ur because we have a plane like this. Okay, so and then we assume that the molecule is actually rotate at certain velocity, so its rotation is actually remain in one places, in one level. So that's why there are no velocity component on r axis. if the velocity component of r axis, so this is the r axis, was exists, so means the rotation cannot be circular like this, so it will become bigger and bigger. It will become a spiral path line. Okay, I hope you could understand that one. So again, we don't have the gravity here. So and then we assume that there are no pressure difference, for example. So and then we could u theta d theta, u theta dz, ur d theta is also equal to 0. So and then here the u theta over r. That's what I said previously. The u theta over r here is exists because in this situation, so we have a molecule here with certain velocity, we have another molecule with certain velocity, we have here with a certain velocity. So mean the changes of this velocity will give you du theta over dr. That's why the value of this one is exists. Okay, so I hope you could understand how to determine or how to understand the Navier-Stokes equation. So and then you could do this. So and then if you substitute this one, if you rearrange this equation, everything, so you will have this one, this term. So it's depend on this, and this term. And then it can be simplified like this one. So here, please be careful about this one. Okay, so because all of this term is actually can be simplified into this one. Okay, so what is the meaning of d over del r, u theta over r? So this is the partial differential. So I hope you could understand that we fix something, u theta, and then we have d dr for 1 over r. And then we have 1 over r, and then we have d dr for u theta. Okay, so you could do that, and then you could merge with this one, and then you will get this term. So and then if you 1 over r, okay, and then so again, because we will have the two differential here, so we need to integrate it twice. So for the first time, we will have a 0 here, so it will comes a constant c1 here, and then we integrate for another one, so it comes the constant of c2 here. So and finally, so we get the general equation of this one. So what you need to do is you need to find the constant C1 and C2, and it will depends on the boundary condition. Okay, so and then the boundary condition, so we found that the R is infinity, so the value of U is become 0. So mean this is the R1, so we get the C1 is equal to 0. And then again, so in this situation, we found that the molecule, okay, because we have the cylinder here, the cylinder will rotate at certain speed. So normally in cylinder, when it's rotate, we will use the rotational speed. We will use the rotational speed. And then you need to understand that there are two types of speed. One is rotational speed, and the other one is the linear speed. So because these two speeds is actually totally different, you need to differentiate it because sometimes in basic theory, they will derive by using the linear situation, but in application might be you will have the rotational condition. So the relation between the rotational and the linear speed is U is equal R omega. So and then it is equal to pi dn over 60. So this is the common equation that I think you already know about this. Okay, the u here is the linear velocity, which is the meter per second. The r is the radius, so it should be in meter, and the omega here is the radian per second. So the radian doesn't have any units, so over second. So it's still meter per second. And pi dn here is sometimes when you have a rotational device, okay, you will describe it by using RPM, rotation per minutes. Okay, so and then to convert the rotation per minute to radian per second, or to convert it into the linear speed, so you just use this relation. Okay, and then pi is constant, so d is diameter, so it should be in meter, and n here is the RPM, so mean the rotation per minutes. Because we have per minute here, that's why we need to divide this value with 60. So means it will give you in term of second. So if you have RPS, rotation per second, so no need for you to divide the value with 60. So I hope you could understand this one, because sometimes they will give you in RPM, but sometimes it will give you a frequency. So I think you could convert it from the frequency into the RPM and so on. So it's actually the same things, but this is the common term used in machine. Okay, so if you put everything, so means for example here, so this is the outer surface and this is uh, the lower one. So might be it's the idea is if we the means of r infinity will lead you to the u equal to 0, means might be this situation is actually like this. Okay, the situation is you have a cylinder here. Oh, okay, we have a cylinder here. Okay, and then the cylinder is rotate at certain velocity, and then it will influence the molecule, the molecule of fluid beside that stay near the rotating cylinder here. So to rotate with along this direction. However, the further, the far the distance here, so the influence will become lesser and lesser. That's why we put the condition of if r is become bigger and bigger, so it's go to the infinity, so it's become bigger and bigger, so the u will become lower and lower, and maybe after certain distance the molecule, the fluid molecule here is not rotate to this direction, because the influence of rotating cylinder is actually finished. So the influence is not exist when the distance is too far. Okay, and then if the r is equal to the radius of this cylinder, so it will rotate at u equal r omega. So and then you could do this. So finally we could have C1 is equal to 0, and then we have a C2 is actually equal to r square omega. And then if we substitute to the CR2 here, so we will have the U is actually r square omega over r. So and then, so the question asks us to calculate the pressure. So first, they ask you to calculate the velocity distribution, and the second one is to calculate the pressure. So the pressure here is okay. So it is a trick here. Okay. The trick is, okay, let's say we go back to this one. So we have the Navier-Stokes equation for the x-axis. For the r-axis, so we have the axis of the theta axis, and then we have the axis of the z-axis. So we found that okay, where is the p here? So why we take the, okay, if we see here, okay, I lost the p here, I think. The r should have delta p here. Okay, so they are base here. So why we take the r momentum is actually because the pressure here, okay, the pressure here is different with the location of R. So we just use the Navier-Stokes equation for the R momentum. So we have the dp dr here, and then we try to simplify everything. So I think you know about this. This is the steady state. So we have the gravity is not influenced by the radial axis and so on and so forth. So and then we could simplify this one, okay, into this term, and then what we need to do is we rearrange the equation like this one, and then we bring the r here to the left hand side, and then we integrate. So finally we will get this one, and then after integration we get the constant value. We substitute the boundary condition, and finally we could calculate the pressure as this one. So this is based it is come from the integration of your Navier-Stokes equation. Okay, so means that until this question, so I hope you could understand the first. If possible, please remember the Navier-Stokes equation. Okay, it's very hard, but I try to give you an appendix for the in final exam, because the Navier-Stokes equation for polar coordinate is quite tough, it's quite complex. So but the main thing is, I hope you could understand the meaning of the Navier-Stokes equation. The meaning means that you know what is the physical meaning of du over dz and so on and so forth. Okay, and then you could simplify it, because normally we will describe it in we try to simplify it first, then we solve the problems. Okay, so we go for this one. So this is just a straight forward. I think I take you could read part of this one, because I mentioned the okay, you could get this from the textbook actually. So for 3.8, okay, so let's say we have an air 20 degrees Celsius and 1 atm is driven between two parallel plates 1 centimeter apart by an imposed pressure gradient dpdx, and by the upper plate moving at 20 centimeter per second. So calculate the volume flow rate per unit width if dp over dx is minus 0.3 pascal per meter, and also the value of dpdx, which causes the shear stress at the lower plate to be 0. So this is okay. You can open your textbooks. It is we have around page. So because okay, this might be page 111. Okay, so this is just a bonus actually. A bonus means because in our notes we define it separately. So we discuss about the co-ed flow, and then we discuss about Poiseuille flow. So if you turn to page 110, so we have the combined co-ed and Poiseuille flow between plates. So means that we have moving plates, okay? So but the pressure is actually exists. Okay, according to our basic notes, we found that in co-ed flow, the pressure is not exist, because we assume that it is open to atmospheric pressure, so the pressure is equal to the atmospheric pressure. So we could assume that in normal situation, the gauge we calculate in gauge pressure, so the atmospheric pressure is equal to 0. So however, if your conduit of your pipe is in rectangular shape, so means that and then you could do something in just in closed system. So and then you could have one of the plates is moving at certain velocity. So means now you are combining the co-ed and flow and the Poiseuille flow. So so I just simplified this one. So this is the common equation here. So you could get from the page 111. So I think previously we showed that the velocity between two plates is actually u over 2, 1 plus y over h. So this is in previous note we show about this one. And then if it is combining of co-wave and Poiseuille flow, so we have another additional equation here to show the increment or the changes or the influence of pressure. So we have a pressure here and we have a velocity here and this term. So and then the P here is actually this one. So you could refer to the textbooks, and then if we substitute this, so we could get this value. So and then the question is, if the dpdx is equal to minus 0.3 Pascal per meter, so we do the question asks about the volume flow rate here. So the idea is Q is equal to AV. And now I think you already know why it's start from the U dy, because we are calculate a small flow rate for a small element. So the small element here will determine as U, because U is the component velocity, so meaning the velocity of that particle of that control volume. So and then we times with the Y. So I think you already know about the Cauchy-Riemann equation. We have U here, so this is the dy. Okay, and then we assume that the width here is unity, means 1 unit. So the Q, dq is actually U times dy times 1. So it's become U dy. And then to get the total Q, so we integrate both of these. Okay, we get both of these terms. So now we have a Q is equal integration of U and dy. So this what we have here. So and then we substitute the value of U, okay, with the previous term. So we have this one, okay, and then we integrate with Y. So I think you could do this because the U over 2 times 1 is a constant. So we have another Y, and then we substitute with the H plus H and minus H to give the minimum and maximum location. So we will have this one, and then we could substitute the value, so we could get it is around 0.00238 meter square per second. So please do not confuse with these units, because okay, sometimes we could write the flow rate is in normal one, it is a meter cube per second, because it is show the volume that transfer for every second. But because we assume that the width is unity, mean 1 unit, so it can be reduced as meter square per second. So I hope you could alert about this. So and then here, okay, so here the equation will remain as dpdx here, but please read means please understand that the term of dpdx mean the gradient or the changes of pressure along the axis. So in this situation, they will give you is minus 0.3. So you just substitute the value of 0.3 at the terms, and then you could solve this problem. That's why I say in this first, after you see the Navier-Stokes equation, I hope you could understand the term, because sometimes you need to just define that terms suitable with your application. If you still remember, previously we have the value of dr over dt. So when we derive the continuity equation, if I'm not mistaken, so you need to understand that this is the changes of r compared to the time. So it means that the r is constant, so mean the dr dt is equal to 0. Okay, so so please take care of this one, because this is the essence of the chapter 1, 2, and 3. So and then the value of dpdx, which cause the shear stress at the lower plate to be 0. So so the equation is come from the textbook. You can open with start from page 110. So we substitute the value, so we could get, so it is around 0.0724 Pascal per meter. Okay, so and then again, we need to derive about u, means the velocity. So if you could see, all the question is about to the integration, about the derivation, about the velocity. So let's say we have this question 3.9. So let's say we need to derive the solution of u, y, z for flow through a elliptical duct, figure 3.9 in your textbook. By solving equation 330, begin with the gas quadratic solution u a plus by square plus cz square and work your way through the z solution. Okay, so in this situation, just a little bit just to test your understanding about the axis. So the question give you for u, y, and z. Okay, because usually we will have UR and sometimes it might be YX and so on and so forth. So the difference of here is we assume that in the equation, okay, in the equation of the velocity here, you must have two unknown, means in term of Y and in term of Z. Okay, so because means that the velocity is now changes, will be affected by the location of Y and location of Z. So the Z here is actually the coordinates. Okay, so why they use Z? Because for example, we have an elliptical, so it means the eclipse, okay, the ellipse. So we have this shape, okay, and then this is the length of this shape. So if we, okay, let's say we draw like this. So there is a molecule here, so for sure it will flow on z-axis, but at the same time might be this molecule will go up and down like this. So that's why it has component of z, okay, to make sure that this molecule will go forward like this, and it must have component of y to make sure it could flow up and down. Okay, so something like that. Okay, okay. So it's so the idea of the idea of this question. Okay, so this is given by the question, I think. So they want to show the question here. Okay, so this. Okay, so this is the we need to show the equation of u here is equal k 1 minus y square over a square minus z square over b square. So again, you need to choose your Navier-Stokes equation because Navier-Stokes equation is, I think previously you know about the Bernoulli equation. So means everything that move, fluid that move at certain with certain velocity. So we could calculate the pressure, we could calculate the velocity by using the Bernoulli equation. But now to calculate more details, so we use the Navier-Stokes equations. Okay, that's why we take Navier-Stokes equation here. And because the terms here, okay, in terms here is in Cartesian coordinate. Okay, this might be the flow is more in Cartesian coordinate. They just go forward and they just go up and down. Okay, because there are no element of rotation. So mean is no need for us for to use the polar coordinate. It same goes with the circular pipe. For example, if it flows straight forward here, so you can use the Cartesian coordinates. Okay, so whether for it has the radial and so on, but the molecule is not rotating like this, so we use the Cartesian coordinates. So I hope you understand this one. So and then because the question here is only consists of y and z, so mean the parameter of x is not influenced at all. So means that we could simplify the Navier-Stokes equation for the x. So we have the x direction here. So let's say this is the z direction. Okay, so and then actually it's same. So let's say we have the gravity is not influenced, so it is a steady flow, and then the pressure might be exist. So and then we don't have any du dx, it is steady, and now we have the du dy over dy du du dz. Okay, so and then we could simplify this one. So and then we could bring this term to the left hand side. So here, so we will have this one, and then we could start to substitute the value. So we know the value here is given like this one. Okay. So we substitute the value of u here. Okay, and then if we differentiate it, so we could get this one. So because it is only affected with the y square here. So and then again we substitute with another, so we have another terms here. So and then if we differentiate, so we get the minus 2k over a square. So means that the differential of two value here is negative 2k over b square. So this is the del square u over del z square. Okay, this is for z and this is for y. So we just the difference is only from for a square and the b square here. So and then we solve the problem. So we get the value of k here. So and then we substitute again the value of k here in this one. Okay, so and then we could write the value of u in the full term as this one. So this is the idea to for this question. Okay, so for I think 3.1. Okay, we can go this one. So for question 3.12, so it is desired to measure the viscosity of light lubricating oil. So mu is between 0.02 to 0.1 Pascal by passing approximately 1 meter cube per hour of fluid through an analysis of length 30 centimeter with inner shown as B, and the outer radius shown as A of 9 millimeters and 10 millimeters respectively. Estimate the expected pressure drop through the device and appropriate instrument for the pressure measurement. So here, so the ideas of the annulus. Okay, I think you could imagine the annulus. So we have the flow that between this ring shaped cylinder. So that's the idea. And then you could refer this with the textbook okay. You could refer with the textbook here. So the hydraulic diameter. So we mentioned it as dH. It can be calculated by 2 times A minus B. So A is the outer one. So the larger one is 10, and okay, and the inner one is 9. So you could get 0.002, and then you could calculate the area here. Okay, and then I think you already know we calculate the larger area first, and then we deduct with the smaller area. So we get this one. So the average velocity. So this is the common equation for the continuity equation. So we get it is around 4.65 meter per second, and then we could calculate the Reynolds number. Okay, so here why in the first place we need to calculate the diameter, the hydraulic diameter, because normally if you have a flow in pipe here, okay, the water will flow completely, fulfill the area of this pipe. But in annulus and in annulus here, so only, okay, only the ring area is flow, water will flow only at this ring area. So that's why we cannot calculate the Reynolds number by using the common rho Vd over mu, but we need to use the D here is the hydraulic diameter. And the hydraulic diameter is actually depend on the situation. Okay, so in this case, so the equation is given is 2 times A minus B. So we just use the equation here. We substitute the Reynolds number, so it's we can get it is between 83 to 418. So how we could get the 100 of 418, because we have the mu here is between 0.02 and 0.1 Pascal. So if you substitute 0.02, you will get 83.7, almost this value. And if you substitute the 0.1 here, so you will get 418. Okay, so that's the idea where I just do this. So and then this is the equation from the textbook. So it's 3.51. So we have this one, and then we again we could simplify this equation as for sure we have delta dp over dx here. So because previously in many situations when we have dp dx, we need to bring the x here to the left hand side, and then we need to integrate them to get the final equation. But as I said, sometimes to solve a problem, you need to understand the meaning of that term. So in this case, so the dp dx is actually to showing you the difference of pressure along the x-axis. So we could replace the dp dx with the delta p over L here. So and then if we substitute with the equation, I think, okay, we have okay, I'm sorry. Okay, so then I thought we need to substitute the delta p. Okay, so means that we could rearrange this equation, then we could calculate the value of delta p, because all the value here can be calculated, can be substituted and solved. Okay, however, please make sure that you will calculate it on SI units. For example, we have 1 meter cube per hour, so you need to change with 1 meter cube with 3,600 seconds. And then you need to replace the 9 millimeter and 10 millimeter to in meter unit. So and then a Pascal second, it can be stay with that one. 30 centimeter need to be converted with 0.3 meters. So and then if you substitute that one, you will get it is around 343. If you use the lower value of mu here, okay, so and then if you use the highest one, 0.1, so you will get it is around 1.68 megapascal.